All right, so we are in Introduction to Statistical Learning, Chapter 10, and this is question number 5, which I think is the last conceptual question. Okay, so here's the question up here. So in Table 10.2, which I've copied and pasted just below that, on page 433, we see that the ordering of three methods with respect to, let me just read it. We see that the ordering with respect to three methods, the ordering of the three methods with respect to the mean absolute error is different from the ordering with respect to the test set R squared. How can this be? Okay, so the three methods that are being discussed here are these three models in the table: linear regression, lasso, and neural network. Okay, and for each of these on the hitters data set, all this is explained around page 433. But we have a mean absolute error as well as R squared value conducted on the test set of data, right? So these are both being done on the test data as opposed to the training data, right? And if you rank these, you get a different ranking, okay? And so I'll show the rankings below here. But remember that that a better fit model for mean absolute error is going to have lower error, but a better fit model with R squared is going to have a higher R squared. So so that little bit of mental reorganizing and shuffling is sufficiently complex that you probably want to write it down just to convince yourself, but I've done that in the table down here. So I have the best model to the worst model for both measurements of fit, as well as the number of parameters that they have here. And by mean absolute error, meaning the lowest error, we have lasso followed by linear regression followed by neural network. But now if I look at the test R squared, the order changes to where now linear regression is best, neural network is second, and lasso is worse. So the question is, why would these two types of fit metrics, I guess I'll call them, why would they differ? Why would they differ, like when we're ranking different types of models? Okay. So I think that the major reason for this is that the MAE and the R squared, well, they're measuring different things. Like they're both measuring fit in a generic sense, but the mean absolute error it's the absolute error. It's the average absolute error across all observations. Okay, whereas the R squared is penalizing like the square of each error. Now it's a little bit more complicated than that, right? Because it's comparing that to the variance in the data and all sorts of things, but at its core, it's penalizing according to the squared size of the error. And so what does it do when you square the size of the error or of anything? Well, what it does is for errors that are larger than 1, the size of the squared error gets super linearly larger, right? And for errors smaller than 1, they get smaller. Okay, smaller than the rate at which the absolute size of the error is decreasing. Right. So I hope that makes sense. Right. And so depending on how these errors are distributed in the in the data relative to the fit of the model, just the error sizes are going to vary, and if it has a lot of large errors, well, those errors are going to explode in size and really drive down the R squared, potentially. Whereas in the MAE, they may not have as much of an impact. Okay, and conversely, if a lot of those errors are less than 1, well, now the R squared is going to be doing probably better than the MAE, right? So in other words, I think that the large picture here is that, well, yeah, of course they're giving different rankings because they're measuring fit in very, very different ways. I think that's the core of the answer here. Okay, we'll call that good.